In this video, we're going to talk a little bit about what happens when a line is tangent to a circle. And the line tangent to a circle means that the line and the circle only have one common point. And usually a line and a circle don't have a common point, or they have two common points. A very, very important property is that if we take the center of the circle and we connect it with the tangency point, then this angle here is actually 90 degrees. Like, suppose you put a ball on the ground and it just sits there. Well, then the whole picture is symmetric with respect to this line here. So in no respect can this angle be somewhat different than this angle. And therefore, they both have to be 90 degrees, because their sum is 180 degrees. Now suppose I draw another line that is tangent to the same circle, then this angle is 90 and this angle is 90. And let's see what we have about this quadrilateral here. Well, we have that this segment equals this segment because it's a radius, and therefore this right angled triangle is congruent to this right angled triangle, because they share the same angle of 90 degrees, and they share the length of this side, and they share the length of this side. And the angle they share lies against the larger of the sides. So this side is larger than that side. So we got some properties here. First of all is that this angle equals this angle. And so we have an angle bisector right here of this angle. Second of all, we have that this segment equals this segment. And so we got these two important properties. If we have a circle and the point outside of the circle, we can draw two tangent lines with respect to the circle. And then if we connect the center with the point, then there's an angle bisector here. And the second important property is that the lengths of these tangent segments here and here are equal. Furthermore, this point and this point are symmetric with respect to this line, and so this angle here is 90 degrees. So this line, we say it's perpendicular to this line. And what's more, we have that this angle is 90 plus this angle makes 180, so this quadrilateral is cyclic. And therefore, we have that this angle here we can mark like that, and this angle here we can mark like that, because of course this angle equals this angle in a cyclic quadrilateral, and this angle equals this angle also. And finally, because of the symmetry, we have that the length of this segment equals the length of this segment. So this is the setup for the optional problem. We have two circles with radius r, so they have the same radius, and we draw this tangent line like this, so it's tangent here and tangent here, and this line, which is tangent here and tangent here. The next step is to draw this circle, which is tangent to these two lines, here and here. And finally, we draw this line and this line, which are tangent here, 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 and here to the given circles. And what we need to prove is that this angle here equals this angle here. So I'm going to denote them with alpha and gamma. And here's the solution. First of all, I'm going to take the center of this circle, and I'm going to connect it with this point. So that's how I get the dashed line. And now we know from the property that we just derived that this angle equals this angle. So this is an angle bisector. Now I'm going to draw this tangent line here that is tangent to this circle here and this circle here. Then these two lines are actually symmetric with respect to this line. Now I'm going to explain why. Well, first of all, this line and this line are symmetric with respect to the dashed line, because this line, its image, is a line that passes through this point, such that this angle equals this angle, and so this is the image of this line under the symmetry with respect to the dashed line. And because this circle and this circle has equal radii, and they are kind of inscribed within these two symmetric lines, then this circle and this circle are also symmetric, or mirror images, with respect to the dashed line. Furthermore, the dashed line passes through the center of this circle, and so this circle itself is symmetric with respect to the dashed line. And so all the three circles are symmetric with respect to the dashed line. And so these two tangent lines are symmetric with respect to this, because they're tangent in the same way tangent to circles that are symmetric. Now, because of the symmetry, we can mark this angle here as alpha. And now let's consider another symmetry with respect to the green line here. Well, we have that it passes through the center of this circle and the center of this circle. That's how we define the green line. And so this line here and this line here, which are tangent lines to both circles, must be symmetric with respect to the green line, because they're tangent to circles that are themselves symmetric with respect to the line. Furthermore, this line and this line are also symmetric with respect to the green line, because they're tangent, again, to circles that are themselves symmetric. And therefore, this angle here, alpha, and this angle here, gamma, are symmetric angles. This point and this point are symmetric with respect to the green line. This line is symmetric to this line, and this line is symmetric to this line. So if we took this angle and we made the mirror image with respect to this green line, it would coincide with this angle here. And so alpha equals gamma, as desired. It's interesting to see the facts that we derived along the way. For example, that the green line passes through this point, and it also passes through the intersection here of this line and this line. We also have, for example, because of the symmetry, that this angle equals this angle, and this angle equals this angle, and also we know that this angle equals this angle.